So, in starting chapter 2, one of the things that we're going to talk about here is actually something that I personally think is fairly interesting, and that is some of the early laws that were developed in science. It's not something that we use necessarily a whole lot in our day-to-day chemistry, so we're not talking about it in class, but it actually was fairly important in terms of developing the things that we use now. So we're going to talk about it here instead of in class, but it actually is pretty important. The ancients, if I can spell it right, philosophers and things like that, they observed the world around them, okay, and they made observations, and they used it as a way to, talk about the world, and they were trying to figure out how things work, just the same way that we do. They didn't always get it right. People like Aristotle, okay? He thought that, I take a cup of water and I can split it in half. I get 2 half cups, still water. Split it again, I get 2 quarter cups, still water. He thought that everything could be made infinitely smaller. That there was no smallest piece that could be found. There were others who disagreed with him. One in particular was a guy by the name of Leucippus, however you say that. And he said, we can make things really, really small, but there has to be a smallest piece. Okay, which was 2 different modes of thought. They debated each other. In general, we know more about Aristotle. Aristotle's idea is one. For a long time, people thought that we could always divide things infinitely smaller. Okay, but again, it was all mental exercises. It wasn't until the 1600s, 1700s, when we started having alchemists. Not really chemists yet, but alchemists who were trying to find elixir of life, something that would let them, potions that would let them live forever. Everybody wants to do that, right? Or that would turn base metals like lead and iron and stuff like that. But they wanted to turn base metals to gold. Okay, and so instead of just talking, they were doing, okay, and they were mixing things. And one of the keys, though, of the alchemists is they recorded their observations and the types of things that they did. Okay, and so they were the first ones who described things like filtering and decanting and distilling, and a lot of the different techniques that we use now, they actually used back then. But the big key was that they didn't just talk about it, they did it, and they recorded their observations. So it gave us something that we could go back to over and over again. Well, you did this, and this is what happened. And you did it again, and it happened again. And you did it again, and it happened again. And people started to see that, okay, things are different, and started to use these observations, use these trials and errors to start to really, truly get an understanding of what matter really was like, okay? And with that came a change in how we thought about matter. The first big new law that came about was given by a guy by the name of Lavoisier. Okay, Lavoisier is known as the father of modern chemistry. He came up with this particular law in 1789. I will say you do not have to memorize names and dates. I will say names and dates so to help prod memories and things like that, but I'm not going to say what year did Lavoisier discover the law of conservation of mass. I want you to understand what the laws mean and how they figured them out, not who wrote it in what year. Okay. But what Lavoisier was doing was he actually was doing an experiment that others had done before him. They had a compound named mercuric oxide, and it's kind of a reddish-brownish powder. And one of the things that they did, late 1700s, they were trying to figure out what everything was made up of. And it was known that if you take sunlight, I have yellow, I can make a pretty yellow sun. Okay, and shine sunlight on your compound, because of course we don't have a lot of electricity and things like that like we do now, that you could take this mercuric oxide and it would change. Okay, you would get a pool of liquid mercury. Okay, and he wasn't the first one to do this, okay? And they observed the change in color and the change in texture. We went from a powder to this nice silvery, shiny metal, liquid metal. One of the things that had been observed was that, say you start out with 1 gram of mercuric oxide, when you were done, and the numbers are going to be off here, but let's say you wound up with 0.8 grams of mercury, okay? And what was assumed was that you destroyed matter. You start out with 1 gram of matter, you wound up with 0.8 grams of matter, and so somehow in the course of doing this experiment, you destroyed matter. Okay? What Lavoisier did that was different is he did it under a closed system. So essentially he put a bell jar over it, so he was not only weighing, this is my little balance here, he was not only weighing the solid, he was also weighing all the gases that were above it. And when he did that, okay, what he found was that the final mass was not 0.8 grams, the final mass was still 1 gram. Because what they hadn't been able to measure before was the gas that was coming off. Okay? And so if you took into account everything that was present at the beginning of the reaction and everything that was present at the end of the reaction, you wound up with the same amount. Okay? And this led to what is known as the law of conservation of mass or of matter. Okay? And what it says is that matter cannot be created or destroyed. It can only change form. Which we mentioned a little bit with energy, but we're saying it again. All right. Very, very important. As an aside, Lavoisier did a lot of these things. He did it with little tiny animals. Okay, so he could put little animals in his little chamber. Okay. There's my animal. And he could look at the beginning. We had lots of oxygen. At the end, we have lots of carbon dioxide because he had it trapped in this little chamber and he could determine what the gases were at the beginning and what the gases were at the end. And so essentially he said, in the course of breathing, there is some sort of burning that is going on, okay? Because just like when we burn wood, we start out with oxygen, we wind up with carbon dioxide. This animal that is living, it starts out with oxygen, it winds up with carbon dioxide. There has to be some sort of burning that is going on inside the body. And so he was the first one to suggest that there is respiration that goes on, okay? But that is Lavoisier, father of modern chemistry, and mostly because of this law of conservation of matter, the law of conservation of mass. Okay, but he wasn't the only guy who was doing things. There was a guy by the name of Proust. Oh, I will say, one of the things about Lavoisier, which is kind of interesting, we might have gotten more from him, but he was a Frenchman. He was minor royalty or nobility, and he was guillotined in the French Revolution because he was a tax collector. But anyways, Proust, okay, doing some of the same types of things that Lavoisier was doing, not with mercuric oxide. He was trying to make copper to carbonate. Okay, and what he was doing was he was looking at different types of copper to carbonate. Fairly common substance. He could get it like in England. He could get it in France. He could get it in Spain. He could get it in the U.S. He could make it in the lab. He had lots of sources of this copper to carbonate. And what he was doing was he would take these different sources, and each one he would break down into its separate components. And what he found when he broke it down into the separate components was that he always got copper, carbon, and oxygen. Okay? And he could take the copper and carbon and oxygen that he got off of it, and he could weigh it. And what he always wound up with was that 51% of the mass was the mass of the copper, and about 9.7% of the mass was of carbon, and that meant that about 39% of the mass was due to oxygen. And it didn't matter where he got it from. All of it was always the same mass percent. And looking at things that other people had done, he came up with what is known as the law of definite proportions, or constant proportions, or constant composition. All sorts of names that we have for it. But we're going to use law of definite proportions. And what it says is that all samples of a given compound, regardless of the source or preparation, assuming that it's pure, but regardless of the source or the preparation, have the same proportions of their constituent elements. What this is essentially a big fancy way of saying we can write formulas, okay? Copper to carbonate always has that same ratio because the formula for copper to carbonate is CuCO3, okay? I always have 1 copper, 1 carbon, 3 oxygens. And because they always have the exact same ratio, I can write a chemical formula for copper to carbonate. And this is actually what distinguishes our pure compounds from our homogeneous and heterogeneous mixtures. Pure compounds always have a defined ratio. That is what makes it a compound. It actually comes from the law of definite proportions. And so I can write a formula for that compound because I know that that ratio is always going to be the same. Now, when they were measuring it, they saw it in terms of masses because that is what they could actually measure. But what we now know is the masses are the same because the number of atoms in the compounds is always the same. Okay. Practically speaking, how does that work? Okay. If I have 2 samples, okay, we will call them A and B, that contain only carbon and sulfur. Okay. I got them, I bring them into the lab, and I break them down. Okay, so I measure the amount of carbon and I measure the amount of sulfur. And so A, when I break it down, is 2.4 grams of carbon and 12.6 grams of sulfur. B, when I measure it and break it down, I have 6.72 grams of carbon and 35.28 grams of sulfur. Okay, so obviously they were different size pieces, but what I want to know is, are they the same compound? Okay, is it the same thing, different size chunks, or are they two different compounds? And so what I need to do is I just need to look at, well, what is the proportion of their constituent elements? Are they the same ratio, or are they different ratios? Okay, so for compound A, I can take 12.6 grams of my sulfur, divide by 2.4 grams, because I like numbers bigger than 1. I get a ratio of 5.25 sulfurs to 1 carbon in terms of mass. Okay. For compound B, I take my 35.28 grams of sulfur, divide by the 6.72 grams of carbon, and I also wind out with 5.25 grams of sulfur to 1 gram of carbon. Okay. They have the exact same proportion, therefore they are the same compound. I don't know exactly what it is at the moment, but I do know that they are the exact same compound. Okay, so that was the law of definite proportions. It was proposed by Proust in 1797. Okay, the next law was one that was proposed by our Quaker school teacher, Dalton. Okay, and he proposed this in 1804. And what Dalton was doing was he was looking at different compounds. And what he realized was that it was possible to get different ratios. So, for example, he could look at water, and he could look at hydrogen peroxide. Okay, and the water, what he saw was that it was made up of hydrogen and oxygen. Okay, we had 2 grams of hydrogen to 16 grams of oxygen. For the hydrogen peroxide, again, it is hydrogen and oxygen. Still 2 grams of hydrogen, but now it is to 32 grams of oxygen. Okay, and this kind of was against what Proust was saying. Proust was saying if I have these elements, they can only combine in certain ratios. And what Dalton is getting is he's getting 2 different ratios. Okay, he has the exact same elements, but he has 8 oxygens to 1 hydrogen for a mass ratio, and in another one he has 16 oxygens to 1 hydrogen for the ratio. Okay, so same compounds, 2 different ratios. Okay, what he came up with, therefore, was the law of multiple proportions. Okay, and what that says simply is that elements can combine in different ways to form different compounds. All right. These different compounds, the mass ratios are small whole number multiples of each other. Okay, so if we go back to our water and our hydrogen peroxide, we have 2 different ratios. Each one has its own. Okay, the fact that my water is 8 oxygens to 1 hydrogen, that mass ratio, doesn't matter what water I have, it is always that mass ratio. The formula for the water is H2O. Okay, and so the water in and of itself obeys the law of constant proportions or definite proportions. Okay. My hydrogen peroxide has a different ratio. It has a different formula. Okay. And so each one of these has its own ratio to satisfy the law of definite proportions. Okay. And then what we have is that the ratios are a multiple of each other. And so what I can do is I can take my hydrogen peroxide to water, okay, that is my 16 to 1 over my 8 to 1 ratio, I wind up with 2, okay, which is reflected in those 2 oxygens. And so that is my small whole number multiple of each other. My ratios are a multiple of 2, okay, so one is, the mass ratio is twice what the other one is. And that is reflected in that subscript 2, that these are small whole number ratios, and essentially what he didn't know it at the time, but it is reflecting the different numbers of atoms that can combine. I can have 2 oxygens, I can have 3 oxygens, I can have whatever. These different numbers of atoms that can come together are going to give slightly different formulas, and because our formulas are whole number multiples of each other when we write them, our masses are going to be small whole number multiples of each other when we write them. Okay? So again, I can look at 2 different compounds. I can look and see, are they the same compound, yes or no? If they are not, then I can figure out what is that whole number ratio by just taking the 2 and dividing them. Okay? So that is the law of multiple proportions. One of the things, these are going to be different compounds. Okay, when they combine, they are making different compounds. The properties of them are going to be very, very different from each other. So they're going to have different boiling points or different melting points or odors or colors or tastes or chemical properties, things like that. Okay. Dalton did then combine all of this together in his atomic theory a few years later. Okay, so 4 years later, we got Dalton's atomic theory, which kind of brought together everything that had been determined thus far. What Dalton did, he explained everything that was known thus far. It wasn't 100% correct, okay? But it was close enough that we still keep it, okay? First thing in his atomic theory was that each element is composed of a tiny indestructible particle. Which he called an atom. Now, Dalton's picture of an atom is not the same as what we picture an atom. He envisioned a solid ball, kind of like a marble or a rock. Okay, and this solid ball could attach to other solid balls, some way, shape, or form, to give us our compounds. Okay, so we have these atoms, these balls. All atoms of a given element have the same mass and other properties. That distinguish them from the atoms of other elements. Now this is where he wasn't quite accurate. Again, back then what they were doing was they were making mass measurements. Okay, so he saw that, oxygens weigh 16. hydrogens weigh 1. Whatever. He measured a mass. They could not measure them so as precisely as we can. And so it looked like all oxygen atoms, doesn't matter if they're in water or hydrogen peroxide or a protein or whatever, all oxygen atoms weigh 16. All hydrogens weigh 1. We know now that it is not the mass that distinguishes them. It is the protons. And so the way he wrote it, or the way he said it with the same mass, that part's not correct. But the overall idea that there is something about the atoms of one element that distinguish them from the atoms of another element is true, and so we keep it. Okay. Next is essentially the law of definite proportions. Atoms combine in simple whole number ratios to form compounds. And different ratios give different compounds. Okay, and so this is essentially our law of definite and multiple proportions. Okay, in a nutshell. Okay. The last thing is that atoms of one element can't change into atoms of another element. Okay. Now we know that that's not totally correct. We now have nuclear radiation and bombardment and things like that where we can smash things together and they will change. Okay. Radiation, nuclear chemistry, those types of things weren't around. Well, they weren't known in 1808, and so they didn't know that you can change them. But generally speaking, under normal chemical conditions, we can't change atoms of one element into another element. And so what happens then in a chemical reaction is that atoms change the way they bond. Okay, and in doing that, they formed whole new substances. Essentially here what he is doing is he is restating the law of conservation of mass. Okay. So this takes us into the early part of the 1800s, and it sets the foundation for a lot of things that are going to be happening. We still have a lot of people trying to figure out what things are made up of and trying to break things down into the smallest particles. They are discovering lots and lots of different elements, how things are hooked together, different ways of breaking things apart. This is when electricity is being discovered and there's going to be electrical things that start going on. But these were the early laws that we had that set the foundation of a lot of the later discoveries that were going to happen. And so, again, after this point, we really start doing a lot of things with electricity and discovering some of those different atomic parts. Is something that we are actually going to talk about in class. Okay? And so at this point, we will stop for now.